Connectivity in the data center is extremely important, and a lot of it is very short in terms of going within a rack or racks next to each other. So, David, we're going to be talking a little bit about active electric cabling. Could you tell us about what those things are and why they're so important and how we're going to be able to make those things work at 800G?
Sure. Thanks again for your time, Bill. So active electrical cabling. Essentially, these are active cables as opposed to passive, what they call direct attached cables. I think that's copper cables without any electronic components, right? So what we are seeing in the data center is that the data connections between equipment is transitioning from 400 gigabits per second to 800 gigabits per second. And what's happening is that once you double the speed, or if your speed goes up, there's an effect called skin effect. Essentially, what happens with the skin effect from the physics standpoint is that when the speed the data transmission goes up, it gets harder and harder to be able to support that speed in the same copper wiring that's being used as a cable medium. So what we see is that once you double the speed from 400 to 800 gig and future 1.6 terabits, the copper cabling is becoming shorter and shorter, right, and thicker, right? On the flip side of what we're doing with AECs, it's called active, is we're placing what we call a retimer. It's a type of mixed signal SoC that's placed inside the cable to be able to extend the cable link with the copper technology as your speed, transmission speed goes up, right? So that's AECs type of product. And we see this throughout the data center interconnect space, connecting top of the rack switches to any servers, be it GPU, CPU, TPU, a lot of different type of servers being integrated and being deployed inside data centers for AI clusters for all these ChatGPT type of applications.
Okay. So your new announcement is a smart retimer called the P1B121, and it
Mhm.
actually works with 112 gig SerDes. How does that match to the 800 gig we were just talking about?
Sure. So, inside the data center itself, these cables are not just a single pair, right? So to make up an 800 gig AEC, there's actually eight pairs of SerDes that goes into eight different pairs wires. And actually, the actual cable is actually 16 twin X pairs, eight in each direction. So if you take 112 gig times eight, it's actually 898 gigabits per second going in each direction for the cable itself. So the speed itself, if you go down to the channels, right, is actually 112 gig, and there's multiple channels, eight channels in each direction. That makes up the 800 gig active electrical cable bundle.
Now, in terms of implementation, a lot of people have been trying to implement the PAM4 that's being used here using DSPs that I think have been also used in optical modules, but you're taking a different approach.
Oh, absolutely. And this is where, we're taking the purpose-built approach. So if you kind of take a step back, right? So optical cabling technology has been around for many, many years, right? And what's in those optical modules is actually an optical DSP to actually take care of the impairment, the loss over the fiber cabling. So there's a solution in place where other people are taking the optical DSP that they have developed, repurposing that for the active electrical cable or the copper active cable space, right? And yes, that's convenient, but that comes with all the different issues with those PAM4 DSPs from optical space, where it consumes a lot of power, right? Costs a lot and adds a lot of latency to the overall interconnect function within a data center. We are taking a different approach, what we call really a purpose-built mixed signal SoC specifically for active electrical cables, right? We call that BER aware architecture. And the difference in that architecture is that it's still a traditional mixed signal architecture, meaning we have a lot of analog circuits. But what we add is a digital engine that's able to monitor every single analog circuit within our design, right? And actually auto-calibrate in real time due to changes in voltage, temperature. In that way, we can actually produce the same type of BER or bit error rate performance as a traditional optical DSP, but we can do it at half the power, okay, 15 times lower in latency and much lower in cost, right? So specifically, it's purpose-built for the AEC application.
Excellent. Now, You talked before about 1.6 terabits. Are we going to be able to achieve that using this approach and the same type of cabling, or are we going to have to look at something different?
Certainly you can throw a lot of electronics and a lot of computing power into the same application. You can extend the AEC using optical DSP into the next generation 1.6 terabits, where the SerDes speed is 224 gigabits per second. But point two, we actually have a different approach, completely different approach, what we call eTube, right? eTube essentially uses the RF data transmission over a plastic dielectric waveguide. It's a brand new technology that the industry hasn't seen. And what we see is that once the data transmission speed, the SerDes speed transition from 112 gig to the next generation 224 gig, what you're going to see is that copper cabling is just not physically feasible to be able to support the cable reach required for the in-rack and adjacent rack use case, right? Yes, you can put the optical DSP again into the same application, but the
Hmm.
power consumption is not coming up, right? Latency is going to get worse, and it's got to get a lot more expensive. eTube essentially is a perfect replacement for copper because we're going to be able to do it very similar to the cost structure of copper cablings today, but we can actually provide the same solution for 1.6 terabit at 3 picojoules per bit. Okay, what that really means is that you're going to get a very, very low power consumption. In fact, it's 50% lower than the best optical technology that's out there today. And then 3 to 4 times lower in cost and 1,000 times lower in latency, right? So we believe once you get to the 224 gigabit SerDes, 1.6 terabits, or future 3.2 terabits, the eTube solution, we're adding one more category called the active RF cable will be a better solution for 1.6 terabits and beyond. And that's what we're going to be focusing on as well.
Well, we'll be talking with you about ARC in the future. Thanks very much.
All right, thank you.